minus 2x squared minus x plus 2 like you have here in the graph. If you want the derivative of f at the point, let's say 2, the point 2 here. So in order to do that, you need to compute f prime x first, right? From Cal 1, you get 3x squared minus 4x minus 1. Everyone can do this, and then you can plug in number 2 here at the end. So you're gonna get the number you want, which is 12 minus 8 minus 1, which is 3. Well, before you head to function of 2 variables, you have to be expert in differentiation on 1 variable. So if I ask you to differentiate polynomials, if I ask you to differentiate sine and cosine function, if I ask you to differentiate e to the x function, you should be able to do that. Does it make sense? That is the background that you need to have. And in Cal 1, we already know that the geometric interpretation of derivative. So you know that the geometric interpretation of derivative, this is the slope of the tangent line. Right, this is what you learned from Cal 1. That if I want to find f prime 2, so f prime 2, this is 3, but if you look at the picture, what does it mean by f prime 2? F prime 2 here in the picture, this is the point x equal to 2, right? The one that I just make a big dot in the picture. If you look at the tangent line, the green line here, this is called the tangent line. This is going to be the line that touch the curve f at the point x equal to 2. This is called the tangent line. If you look at the tangent line and you want to find the slope of the tangent line, this is going to be f prime 2. This is the meaning of derivative in calculus 1 in 1 dimension. So again, for today lecture and next lecture and a little bit on next week, we are going to talk about derivative, but we're going to extend the idea into 2 dimensions. So what are you going to learn is you are going to learn how to compute derivative in 2 dimensions by using definitions, and you're going to learn it how to compute it by using formula. And then you need to talk about how to interpret derivative in 2 dimensions and also application as well. All right, that is the big picture that we are going to learn in the next few lectures. Does it make sense? All right, next we are going to look at how do we define the derivative of the function of 2 variables. So how? So of course, when you have the function of 2 variable f, x, y, you have x and y. So the idea is so simple. So you're gonna let this thing to be c first. Well, the idea is so simple. So in order to find the derivative, so the idea is, why don't we fix 1 variable? So if we fix 1 variable, then the function of 2 variable gonna go back to 1 variable, right? And that you can use all the theory from 1 dimensional calculus. So let's fix y equal to b, where b is just a constant. So you're gonna fix y equal to b. So just fix y to be a constant. So where b is a constant. So once you fix y equal to b, so what you have is, then we have c equal to f x comma b. So here you're gonna have only 1 variable left, which is x. B is just constant, so you're good now. So this is just a single variable function, right? So when you have a single variable function here, well, then you can use all theory that you learned in calculus 1. to this function fx comma b. Well, by this I mean if this function has a derivative at the point x equal to a, then we call it partial derivative with respect to of f first, partial derivative of f with respect to x at the point AB. Well, this is a definition. So in order to define the derivative in 2 dimensions, you need to fix one variable first. Once you fix one variable, then you're gonna obtain the function in one variable. And then after that, if you take the derivative of that function, so you're gonna get a partial derivative of f. And then you have to specify with respect to what variable. Here, because I fixed y, I am going to have a function of x left. So I'm going to say this is my part. If I take the derivative of this function, this is going to be partial derivative of f with respect to x. So notation is going to be this notation, curl f over curl x. So before you use df over dx, like in calculus 1, this is just in 1 dimension, but in 2 dimension, you're gonna change it to, just make it curve a little bit. So this is called curl f by curl x. At the point AB, this is going to be, well, you see the definition here. So before you have one variable, right? So here you have a function of 2 variable. So you fix b. So you didn't change anything at b. So you just change from a, b, you're gonna go to a plus h, and then you over h, and then limit h go to 0. This is actually the real definition of partial derivative with respect to x. For partial derivative with respect to y, so you're gonna do the same thing, but for partial derivative with respect to y, you're gonna just start from the point AB, and then you fix A, and then you're gonna go from B to B plus H, and then over H. So this is actually the definition of partial derivative. Sounds good? Well, so far, this is going to be so abstract, right? So most of you, well, I think have a hard time to follow the definition here because it looks so abstract here. But keep in mind that when we do the problem, we're going to use the formula. So we learn definition here, but because the definition reduce the function of 2 variable to a function of 1 variable, because, well, before you define partial derivative, you fix y equal to b, or you fix x equal to a first. That means all the work that you learn from calculus 1, you can use it. So that means you can use the formula when you compute the derivative. So before we start doing examples, so we're gonna look at notation first. So this is the notation of partial derivative with respect to x. So partial derivative with respect to x, the notation is curl f over curl x. Sometimes people are gonna say f sub x, this is the same thing. Or sometimes people are gonna say d1f and sometimes people are gonna say d curl c by curl x, for example. Well, if you say at the point AB, this is going to be diff f with respect to x at AB. This is at AB. This is at AB. This is at AB. This is all notation. Sometimes you're gonna see this, and then you say, hey, x, y equal to AB as well. So this is the same thing. This is called partial derivative with respect to x. For y, so you're gonna have partial derivative with respect to y at the point a, b. So this is going to be curl f by curl y, right? And then at the point a, b, and then f subscript y at a, b. Or you're gonna have the subscript to, the subscript to f at a, b. Or you have curl c over curl y at the point x, y equal to a, b. Those are the same notation. It means partial derivative with respect to y. So this is all the theory. We're gonna start doing examples soon. So let me look at the chat first to see the questions. So I have a question from Purohit. He asks, can you please explain what part is with respect to what? So, well, I will go back to the definition again. So when you compute derivative, here we call partial derivative. We need to say partial derivative because this is, we are working with function of two variables. And then when you take derivative with respect to x, when I say with respect to x, that means you differentiate with respect to x. That means you have to keep y fixed. So if you differentiate with respect to x, that means y fixed. And then you just differentiate with respect to x. So that means the value of y, which is b here, gonna be fixed. And then you need to just start from a, and then you go to a plus h. That what does it mean by definition of derivative? And then if you are talking about partial derivative with respect to y, that means x fixed, right? And then when you look at the definition, it's gonna be like you fix the x value, which is a, and then what you move is just going to be from b to b plus h. This is the definition of partial derivative. Well, let's look at example. For those of you who are so confused in the first 20 minutes because you cannot follow the abstract thing. So let's look at example. So you get better when you see example for sure. So let's look at example here. So I want to find partial derivative of the function fxy equal to this thing. So in order to find the partial derivative here, so if the question asks you to find partial derivative, you need to compute the partial derivative of f with respect to x, and you need to compute the partial derivative of f with respect to y. When you compute partial derivative with respect to x, well, keep in mind that here you need to view y as a constant. Because you differentiate with respect to x, so you will gonna be just your x is going to be your variable. So you can view y as a constant. So I'm gonna differentiate x to the fourth power first. Well, because this is go back to one-dimensional calculus, so I can use the formula. So differentiate x to the fourth power, so I'm getting 4x cubed, and then I differentiate 3x square y. So here, what I'm gonna do is, because 3 and y, they are constant, so I'm gonna pull out constant here, 3y, and then I differentiate just x squared, so I get 2x. Does it make sense? You do not need to differentiate 3 and y, right? Because these are constant, so you just pull it out, so you get this, and then you differentiate x squared, you get 2x. And then the next term, you have y times cosine x. Well, the sign going to be negative first. So negative here, you have y times cosine x. Y is constant, so you just keep y there. So you do not need to differentiate y. And then differentiate cosine x, so you get negative sine x. right? Differentiate cosine, you get negative sine. And then constant, you differentiate, you get 0. So at the end, you just simplify a little bit. So you get 3x cubed plus 6xy plus y sine x. This is your answer. Pretty simple and easy, but well, keep in mind when you differentiate with respect to x, you can view y as a constant. The same thing, if you differentiate with respect to y, you can view your x as a constant because, you know, you differentiate with respect to y. So that means for x to the fourth power, when you differentiate, you get 0, right? Because there's no y there. And then when you differentiate 3x squared y, so you're going to get just 3x squared. Does it make sense? Because you have 3x squared y here, right? The one that I just used the laser here, 3x squared y. So your 3x squared is just a constant, but your y is just variable. So you just differentiate constant times y, you get that constant. And then another one, you get negative cosine x, right? Because you have negative y cosine x. That means you differentiate with respect to y, so you get negative cosine. And differentiate sine y. Okay, I forgot sine y on the top one, but it's 0 anyway. So I have sine y, so differentiate sine y, I get cosine y. And then constant, I get 0. So at the end, I have 3x squared minus cosine x plus cosine y. Well, I hope you can follow this thing because you need to know how to find the partial derivative. And it is pretty simple. Well, as long as you know how to differentiate in one dimension. So the new concept that you learned today is if you want to differentiate with respect to x, just keep y fixed. And then you just will y as a constant. You just differentiate like that. And then after that, you learn how to differentiate with respect to y, which means this is the case that you're going to view x as a constant. So let's do one more example before we move on. So example 19, this is going to be a little bit harder compared to the previous one. Suppose that you have fxy equal to the product of these two things, x squared plus 2y squared and square root x squared minus y squared. Well, I want you to find this notation f subscript x add to 1. So this notation means partial derivative with respect to x, because it's just, f and then subscript x. So this is partial derivative with respect to x. And then to 1 here, just once you compute, you evaluate at the point to 1. All right, let's see how to compute this thing. So, well, first of all, I want to compute fx first, and then I just plug in the number 2 and 1 after. So in order to compute partial derivative with respect to x here, so I need to view y as a constant, right? But you can see that you have x here, x squared, and then you also have x here, x squared and the square root. So you have x here and here. So that means this is a product of two things. So you need to use the product rule. So if you recall from calculus 1, if you have a product u times v, well, I recall the product rule from cal 1 for you. If you have uv, right, and then you want to differentiate, so you're going to get u dv plus v du, right? Just from cal 1, Here, we're going to do the same thing. So we're going to say that we're going to keep x squared plus 2y squared. And then we're going to differentiate with respect to x, square root x squared minus y squared. And then plus square root x squared minus y squared. And then we're going to differentiate x squared plus 2y squared. Well, this is just using the product rule. All right, sounds good. Well, again, if you cannot follow me, I think today I went pretty slow. So keep in mind that this is super slow now. So the light blue one, and then differentiate the yellow one, and then plus the yellow one, and then you differentiate the light blue one. Well, this is just the formula for the product rule. And then after that, you just have x squared plus 2y squared here. Well, this is okay already because it's you do not need to do anything because it's outside the derivative side already. So you need to differentiate the yellow term with respect to x. Well, in order to make it easier, so you're gonna differentiate x squared minus y squared raised to the 1/2, right? When you see square root, the best way to differentiate just you know simplify it to something to the 1/2, and that would be easier to differentiate. So on the bottom, on the next term, we're gonna skip it a little bit. So I'm gonna do the first term first. So x squared plus y squared, and then I differentiate that. So I'm gonna get 1/2, and then x squared minus y squared, and then 1/2 minus 1, right? This is by the power rule from calculus 1, and then you have to differentiate inner function. So which means you have this thing again by the chain rule in Cal 1. Does it make sense? Because you remember calculus 1. So when you have differentiate something to the 1/2, so you get 1/2 that thing to the 1/2 minus 1, and then you have to differentiate that thing again. Well, and then, well, I'm gonna simplify the first term first. 1/2, and then this is going to be x squared minus y squared to the negative 1/2. And then you differentiate this, the last term here, with respect to x. That means you're gonna differentiate this thing with respect to x. So differentiate to x squared, so you get 2x. Differentiate y squared, so you get 0. The reason why you get 0 on the second one, because you differentiate with respect to x, y going to be just constant. Sounds good. I simplify a little bit. Well, I do not need to simplify, just at the end, I'm going to plug in number 2 and 1, and that's all. But let's do the second term here. So the second term, I have square root x squared minus y squared, which is already good. And then you have differentiate that term, which is you differentiate x squared with respect to x, right? So you get 2x, and you differentiate 2y squared with respect to x, so you get 0 because y is constant. Well, on the second term, this is just pretty simple. So you have that. All right, so you are ready to plug in numbers now. So why not, right? Fx add to 1. This is plug in 2 square plus 2. Okay, 2 times 1 square here, and then 1/2. X squared is 4, y squared is 1, and then there's to the negative 1/2, and then times 2x, which is 4, right? And then plus 2x, which is 4, and then square root 3. Here you're gonna have 4 plus 2, which is 6, and then times 2, which is well, anyway, you can do it by yourself for sure. This is just the calculation. Well, at the end, you're gonna get 8 square root 3. Well, this is 12 square root 3 over 3 plus 4 square root 3. So at the end, you're gonna get 8 square root 3. So try it by yourself, but this is just the answer for this part. Well, you can see that well, it looks complicated when you look at the slide here, but actually the idea is so simple. When you differentiate with respect to x, just keep y fixed. Well, and whatever you face, you can use the product rule, you can use the chain rule, you can use the power rule, you can use anything you learn from Count 1. Because once you keep y fixed, you go back to a single variable calculus. Does it make sense? Well, I'm gonna do one more example. Well, before I start example 20, I want everyone in this room to check in the chat. So just type in the chat, how would you grade yourself for partial derivative, A, B, C, or D? Well, just give yourself a grade A, B, C, D on partial derivative. After 2 examples, do you understand a lot, or do you have a hard time to follow it? So give me the answer in the chat. So because I want to, check your name too, because I want to see who is in, so I can help you when you have a hard time in final exam. So 22 students here, just please give me the answer in the chat. So and give me the answer in the chat in public, because it's gonna save automatically to my computer. So if you give me the private chat, your name will not go to my computer. So just give me the answer in the chat, not in not public, not in private. Thank you. All right. Most of you say A and B. Well, it seems like you understand it. So let's do one more example to check if you understand it correctly. So example 20. So let's do one more. So fxy equal to x square y times e to the xy. So for here, the question asks you to evaluate curve f by curve y at the point xy equal to 1, 1. So when you read the question for the first time, well, you can see that here, this is a partial derivative with respect to y, right? Because you can see that here, the notation means with respect to y. That means when you differentiate, x is just a constant, all right? We're gonna find this thing first, and then we just plug in that the 1, 1 after, right? The 1, 1 is just the number, the point that you're gonna plug in after. So that means I have to differentiate this function with respect to y. So the function here that I highlight in yellow, this is I just copied from the question. Well, you can see that if you want to make it easier, you can pull out constant, right? So I'm going to pull out x squared outside. This is acceptable because, hey, why not? This is just a constant. Just go away, right? Well, I can pull out x squared outside because that is a constant. So what I have left here, just have differentiate y e to the xy over there. And now, hey, Ajahn, can we simplify more? No, right? So we have y here and we have y here. So we have we cannot avoid product rule. So we're gonna use the product rule again. So x squared and then all right. So here inside the parentheses, so I'm gonna do u dv plus v du. All right, this step to this step, product rule. I didn't do anything fancy, just product rule, right? And then after that, well, x squared and then y. So once you want to differentiate e to the xy, so here, I'm trying to go slow. When you want to differentiate e to the something, so it's going to be e to the something. That is the same thing, right? Because differentiate e to the u, you get e to the u. But because of the chain rule, so you just need to differentiate inner function one more time. Does it make sense? Well, maybe it's just too small, the font. So I'm going to do it one more time. So e to the xy, difference e to the u, you get e to the u. But you still have to differentiate the inner function. All right. Then e to the xy, well, this is easy, just 1. Right? Because differentiate y, you get 1. All right. And that I have x squared times y e to the xy, differentiate y, you get x. Differentiate xy with respect to y, you get x, right? And then plus e to the xy. All right. So this is done for the first part. And then now you just need to evaluate at the point 1, 1. Which is going to be 1 squared times 1 times e to the 1 times 1 plus 1 plus e to the 1. Wow. So at the end, you're going to get, let's see what you get, 2e, right? The answer is going to be just 2e. Well, this is how you compute the partial derivative. Does it make sense? Okay, good. All right. So I hope you find that this is easy Well, this is actually easy because, well, on the exam for sure, I'm going to ask you to compute partial derivative. And this is supposed to be the easy question. Like everyone should be able to differentiate uh, with respect to y or with respect to x easily. The function that you're going to see in this class, well, I'm going to say polynomial, trigonometric function. So if you can differentiate x to the n, sine x, cosine x, e to the x, log x, that would be fine. So we are not going to just do something harder than that. Sounds good? All right, so well, we have about 20 minutes left. Well, about 15 to 20 minutes left. I am going to show you how to compute partial derivative by using definitions. Sometimes, because sometimes I want to test you if you know how to use a definition. As I told you that when you compute derivative, you have two ways to do it. So you can use definition or you can use a formula. The one that we just learned today, we just use a formula, right? Because formula is easy. Well, we learn a lot from Count One, and we want to use formula all the time. But we also need to learn how to use a definition as well. So example 18, example 19, and example 20. These are examples that I use a formula because you know a lot of formula from Count One. However, example 21, this is the one that I'm going to show you how to use a definition. And the question forces you to use a definition because I say that, show that the partial derivative with respect to x is equal to that by using the definition of partial derivative. If the question state like this on the exam or on the quiz, whatever, you have to use definition because I want to test you how to use definition. I didn't test you how to use a formula. If you want to use a formula, it's easy, right? If x is just, well, differentiate with respect to x, 1 plus 0, this is 1. Because you just say, hey, y is constant, done. And then this is the same thing. Well, you can just, hey, if you want to differentiate with respect to y, x is constant, y is not constant, done. Well, this is the method that you can use in real life because, well, if someone asks you to compute derivative, use formula because it is easier. But in theory, well, this is how we use definition. Okay, let's do it. Solution should be about 10 minutes and then we should be good for today. All right, let's look at that. We'll recall that the definition of partial derivative with respect to x, its limit of the function x plus h y minus f x y. Right? This is a definition of well, this is definition. Should say definition. Well, by definition, if you want to compute the partial derivative with respect to x at the point x, y, so it means you start from the point x, y, but you keep y fixed. You just move on the x-axis. So it's just keep y fixed. So y will not change, but x going to change from x to x plus h. And then you compute the difference of these two functions. And then you do the ratio between that difference over h, right? And that will be your definition of partial derivative. So here for question 21.1, so you're gonna do this partial derivative of the function with respect to x is limit of that. Well, I'm gonna copy the definition first. This should be easy and simple, huh? And then after that, I am going to plug in the function. So if x plus h comma y, this is going to be x plus h plus y squared, right? Everyone follow the one that I highlight in orange. I just plug in the function. And then after that, minus x plus y squared, all right, over h. And then if you simplify a little bit, so you get limit x plus h minus x over h, which is actually limit of 1, right? Because it's cancel out, so you get 1. Well, this is how you use definition. You can see that if you use definition all the time, it is going to be hard, because you do not want to do the definition on this question. Who want to do that? Well, if you use definition, it's going to be limit x plus h square y e to the x plus h times y minus x square y e to the x y over h, and then where h go to 0. This is how to compute the partial derivative with respect to x. If you use definition, you can see that it looks terrible, because we don't want to use the definition when the function is super hard, because it's going to be messy. So when the function is hard, we try to avoid definition for sure. We just use a formula. But well, when the function is easy enough, well, I can test you on how to use a definition. So let's do one more, 21.2. So if I want to do here, but with respect to y, so you're going to do limit. When you do with respect to y, it's going to be fixed x, right? But y, just go to y plus h. And that will be limit of, okay, let's do it, x plus, no, x plus y plus h squared, right? And then minus x plus y squared over h, right? This is just plug in the formula of fxy. And then after that, you can see that x cancel out. So what we have left? Well, you have to compute a little bit then. So you have y plus h squared here, and then minus y squared over h, all right? And then you need to expand that square. So you get y squared plus 2yh plus h squared minus y squared over h, and then something cancel out. Well, you're going to have that. The term that you're going to have left, it's going to be just limit of 2y plus h, where h goes to 0, right? And that will leave you just 2y, because limit when h goes to 0 of h is just 0, so it's just 2y. So this is how you use the definition. Does it make sense? All right, so well, you will do the definition. You use the definition only when I ask you to do so. So don't use it if I don't ask you to do, because there will be only one question on the exam that I ask you to do definition, just only one question to check if you know the definition or not. But other than that, you can use the formula. Sounds good? Well, I think we can talk more on another 2 slides, I think, and then we can end the lecture today. So the last thing that we're gonna talk for today is interpretation of partial derivative. You know from calculus 1 that the partial derivative, no, from cal 1, the derivative is just the slope of the tangent line, as I told you. But in 2 dimensions, what does it mean by partial derivative? So again, because the idea is just we fix one variable, right? And then we look at the slope of the tangent line from there. So we're gonna, well, let's do example here. So when I have fxy equal to 4 minus x squared plus 2y squared, if I graph it, I am going to get this surface. Keep in mind that the graph or function of 2 variables going to be surface. If I graph fxy equal to 4 minus x squared minus 2y squared from the computer, so I'm going to get this picture. Well, again, this picture, this is fxy equal to 4 minus x squared minus 2y squared, this surface. Well, when you say you want to differentiate with respect to x, So that's mean you're gonna get 0, right? Minus 2x minus 0. Just go back to the picture. So we have this fxy. So I'm trying to explain from the picture. It's a lot easier from the equation. So when you have the surface here, this is the surface fxy, right? And then when you take the partial derivative, that means you fix y. So let's suppose I fix y equal to 1. This means I fix y equal to 1. When I fix y equal to 1, it means I have a plane that cut the surface. This plane gonna cut the surface. And then when you cut the surface by the plane here, you're gonna get the curve in red here, right? The curve in red here, this is going to be the curve that represent, when you have a plane and then you cut the surface, you get this curve. And then the slope of the tangent line to this curve, this is the partial derivative. The slope of this tangent line, this is partial derivative with respect to x at the point AB. If this point is ABC, the slope of the tangent line is going to be this meaning. Well, you can see that it is not easy to interpret slope of the tangent line in 2 dimensions, but this is actually what it means. So again, if you want to do partial derivative with respect to y, that means you have a surface, but because you fix x, so you just cut the surface using the x-axis here. Cut the surface with the plane here. And then once you cut the surface with the plane, you're gonna get the curve here, right? And then once you get the curve here, the slope of the tangent line to that curve is gonna be the partial derivative with respect to y. Well, just keep in mind that if someone asks you what does it mean by partial derivative in 2 dimensions, your answer is, well, if you wanted to know what it means, you just need to fix one variable first, and then once you fix one variable, you're gonna get a trace or something that the curve after you fix one variable. Well, the book say this is a trace, and then once you have that, so the slope of that trace or the slope of that blue line here gonna be just the partial derivative. All right, does it make sense? This is with respect to x. All right, and that's what I want to talk for today. So on Wednesday, we're gonna start looking at higher derivative. We're gonna look at how to compute partial derivative more than one time, right? Because when you learn Cal 1, you have f, and then you can compute f prime, and then you can compute f double prime, and you can compute f triple prime, and so on. But on Wednesday, we're gonna look at how to do that, because when you differentiate one time, you can have fx and fy, and then you can have fxx, or you can have fxy, or you can have fyy, for example. So you're gonna have so many ways to go for higher derivative. So we're gonna look at how to compute that thing, and also we're gonna look at the chain rule in 2 dimensions as well. All right, so I hope you understand the lecture today, and that is all for today. So again, for today's content, I want you to get the idea about how to compute partial derivative using formula and definition. All right, any questions? 11:55 now. Good. All right. So if you have any question, let me know. We'll know, in the chat or in the line. But if not, you can go. Thank you. Thank you for attending, everyone.